Let's wait for 10 minutes and then we will start the class. Uh, so while we are waiting, the person who asked a doubt last class wanted to ask doubt last class. Shall we take that doubt? Or if there is any doubt that anyone wants to ask, we can take that doubt while we are waiting. So whatever we have done so far, uh, is there any doubt that you want to ask? Okay, no doubt. Let's wait for a minute more and then we'll start. Okay, so let's start today's lecture then. Uh, Share my screen first. If someone can let me know if my screen is visible.
Yes, sir.
Okay, so let's take the doubt first. I think Mutumina asked some doubt yesterday. So if she's there, can she ask that doubt again?
Yes.
Okay, yeah. So what was the doubt? Hello?
Sir, why N is considered for regression?
Oh, why is n considered for regression? Oh, I see, I
Yes,
see.
sir.
Okay, I think I need to open the previous slides. Just a sec. Let me just open my previous slide. One second. Mm, One sec. Okay, so let me reshare my screen. Is my screen visible now?
Yes, sir.
Okay. So what the n here? I'm assuming the n that she was referring is the degree of the polynomial. So remember that we converted our problem into x x bar theta bar equal to y bar, right? And theta bar is the only unknown, and x bar was equal to that each of these x bar has x1 data point, x2 data point, and since there are 11 such data points, it had x11 data points, right? If you do x1 bar into theta, it will give you y1, x2 bar into theta, it will give you y2. So you remember this part, right? Hello?
Yes, sir.
Okay. And these x1 bar, if you remember, these x1 bars that we wrote was these, okay, it was x1 square. So it's a 2-degree polynomial, x1 and 1. Yeah, 1 and 1. So this is a 2-degree polynomial, right? So n came from this part place. So if here we assumed it's a 2-degree polynomial, n equal to 2. There is no such restriction. Why did we assume a second order? Why not we assume like a fourth order? You can go ahead and assume a 4th-degree polynomial. In that case, your x1 bar will become x to the power 4, x to the power 3, x square, x and 1. This 4th-order polynomial, and there is no such restriction. The only thing that came was the order of the polynomial. This was the only hyperparameter. Everything else is not a hyperparameter, right? You just need to decide what is the degree of the polynomial, and once you have decided the degree, then you just simply put x into theta is equal to y, and then you have the answer for theta. So theta is so when you assume it's a degree 4 polynomial, the y hat prediction looks like, assuming it's a degree 4, so theta 4 x4 x is to the power 4 plus theta 3 x cube plus theta 2 x square plus theta 1 x plus theta naught, right? And we just need to find all these theta values, and if we don't know the theta value, we know the degree 4 polynomial. And to find theta value, we converted into x into theta equal to y form, and we were able to estimate theta, and we got theta is equal to theta bar is equal to, can someone remember what is the equation that we got? No one? X
Sir, X transpose X.
uh,
The whole inverse.
4 inverse
X transpose Y bar.
x transpose y bar, right? So you can see this thing,
Yes.
you just multiply x transpose both sides, and this becomes a square matrix, so you can invert this. So x transpose x inverse x transpose y bar. So we got the theta value, and this was the answer. So the only assumption that we made, not assumption, it's the only hyperparameter that we have is the degree of the polynomial. If you can fix the degree of the polynomial, there is no unknown there. There is no other hyperparameter. Is this part clear? So the degree
Yes,
of the
sir.
polynomial is the only hyperparameter that we have. That is the choice that you have to make. That okay, and we also discussed that how do we uh, decide what degree to choose, right? So we will see that we will take that part slightly in more depth and do tutorial on that. Okay, so this part is okay, right? Now I do not have to explain what this x is again. Theta is what is theta and what is x bar, and how did it become x hat here and why it is x bar here. This is all clear, right?
Yes, sir.
Okay, y bar is the known y for the corresponding label x, and y hat is the prediction, like for unknown value of x that you want. If once you have figured out what these theta is, just fit those x into this function, and you will get the prediction. Okay, so let's complete our today's. Let's start our today's lecture. So today we will just take the polynomial regression slightly more in depth. That how do we find the polynomial degree n in different direction. So we have seen that it is not just a linear function like in the previous lecture we saw, but we made an assumption that oh, it's a linear function y equal to some this form. It's a linear function and we are only fitting a line, but we can now make any n degree polynomial and construct this big matrix x into theta vector will give you y vector, and this big matrix x can be a n degree polynomial, right? So it's an n degree polynomial, and it is, and the relationship can be non-linear too. So how do we identify the linear model is a best fit? And we saw the residual plot. Now, so we have, this is for some model, this is model 1, model 1's plot A, model 2, and this is model 3. We are plotting a residual plot. Which model, say a model 1 is say degree equal to some degree polynomial. Model 1 is some degree k polynomial, model 2 is some different degree polynomial, model 3 is a some different degree polynomial. And they say all these three plots are a residual plot, A, B, and C. Assume this is A, B, and C are some residual plots. Which plot do you think is a better fit? Which among these are a better fit? No, I think this is difficult. Let's just assume you have only B and no model 1. A is, there is so many doubts there. So assume there are only two models, B and C, model 2 and model 3. Which model is a better fit? Model B is a better fit or model C is a better fit? Which model will you choose?
Model 2, sir.
Model 2. Why? Because
Yes, sir.
majority of these values are very close to 0, right? Even if some of
Yes.
these values are higher, but compared to this, there are like so many values that are very below. No, it's very difficult too. It's like the values are -1 is also there, and then this is also 0 and 1. Okay, if it is not visible, the numbers are 0 and 1 here. So most of the values here are also less than 1. Most of the values here are less than 2 though. So it seems like model 3 can be also be a better fit. But even though some values have gone to -5, here it has just gone to +5 though, right? This number is 5 here and this is 6 here. So it is in general difficult to say. Both seems to be fair, even though model 2 seems like it's a better model. It's just that the y-axis is not scaled properly. So it doesn't mean that the positive error and this is a negative error. So in general, both model is not so good, but or you can say both models are equally performant. Both models have equal performance. Not much difference there. Is people able to see why I call both models have equal performance, or maybe model 3 has a better performance? Because all the errors are between 0 and 1. Here some errors are between 0 and 2, 0 and -2. Is residual, do people remember residual plot? What are these points? Oh, okay. So residual plot, how do we plot this residual plot? For each x, so for each data point x1, we calculate the residual plot by y hat 1 minus y1. So this is the true y1 and this is the predicted y1 for this particular x1. So this is what we are plotting. For all these points is this error, that for this x1 what was the error? Prediction minus the true error. So this is most of the, if the model is very good, it will, everything should be close to 0. But since the model is not so good, so there you see some error in between. Some have very large error, some have very small error, Some have medium level error. So if majority of the error is very close to zero, you call it the model is good. That's what we are trying to see. So residual plot plots the error in the prediction. Is this okay?
Okay, sir.
Okay,
Okay.
sir.
So in general, we can say the model 3 seems to be doing better. Probably you were not able to see it because the axis is too small, but you can say both models are equally in terms of performance, though you can find a better model too. Okay, so let's look into more other points. So you can see why higher models. Actually, we also saw that higher degree polynomial can actually overfit the data. So which model seems to do better? A 1 degree polynomial, a 2 degree polynomial, or a 4 degree polynomial? Which model do you prefer in these?
2-degree polynomials.
Okay. So people can see why 2 degree polynomial, even though the fourth degree polynomial will have a zero error, almost close to zero error. Both a 2 degree polynomial and 4 degree polynomial, they will have very close to, if you plot the residual plot for 4 degree polynomial, what kind of a plot you will see in a 4 degree polynomial? What in this plot, the fourth degree polynomial, what kind of a residual plot will look like? The residual plot will look like how? How will the residual plot look like? This is zero line. All these points will be very close to zero, right?
Same like zero polynomial.
Everything will be close to zero, right? Because look at your prediction and the true value is exactly on the same line. The blue line is the prediction and x is the true value. It's almost close to zero. It fits properly, right? So the residual plot for 4 degree polynomial is perfectly zero though. So it will be all close to zero. Everyone can see this thing, right?
Yes, sir.
Okay. So how will the residual plot for 2 will look like? Same as 4? No, right? Because there are these points, these small points. I have not on the line. There will be some error because of this, right? So for residual plot, for the first 2 points, the error might be there. Some points might be here, but the remaining points are very close to zero, right? People can see, right? So there are these points are not lying on the line on the curve, so there will be some error there.
Yes, sir.
Huh. So even though there is small error, it doesn't mean that it is a bad model. So residual plot can only tell you that how much gap is there. It should not be a very large gap. But if all the points are very close to zero, you can say that this model seems to explain the data set well. You need to verify more. And this 1 degree model, the 1 degree model will have large error, right? Everyone can see that this will have large errors, right? The 1 degree model. So if you plot the residual plot, the 1 degree polynomial will look like this. Everything away from zero. Maybe some might be close to zero, but most of the points will be away from zero. Correct?
Yes, sir.
Okay. So from residual plot, you can only say that if the model is underfitting or not. You can only talk about the model is underfit. If you see large deviation from zero, you can say that this is not a good model. You need to increase your model complexity. So what do I mean by model complexity? It means that you want to increase the polynomial degree of the model. So you want to increase the model complexity in linear regression. So increase the polynomial complexity. In both degree 2 and degree 4, we have almost similar residual plot. Not same, but similar residual plot. Most of the points were close to zero. When you see most of your points are close to zero in your residual plot, you cannot say that that degree is a good model. You need to verify whether the model has overfitted or. So what do I mean by overfitting? It's like if you see for this prediction, if you have this point, it will suddenly predict that this is the answer, this is the prediction value. But here, if you see, if you predict this, it will predict that, oh, it should be somewhere close between these 2 points. It has large variance. Like for some point, it gives you very high value. For some close by point, it gives very low value. So all these things for this point, you see, it gives you low value now suddenly, right? So even though this residual plots are very close to zero, you need to check for if the model has very high variance or not. If you see that the model has very high variance, which I mean by the very high uh, complexity, when you see this kind of a complexity, like suddenly they will jump above and then suddenly it will go down, sharp changes are there, you can see that this is not the true function though, it is becoming something else. It does not reflect the true function. So the model complexity has become too high, you need to reduce the complexity, and you again reduce the complexity and check if the residual plot looks close to zero, then again go reduce the model function. And if the residual plots looks now very noisy, then you know that okay, n+1 is the degree that you should actually stop at. Remember, this is how we did last time. Like if n equal to 10 fits the model properly, then you should go and check if n equal to 9 fits or not. If n equals to 9 also fits properly, then you should go and check n equals to 8 fits or not. If n equals to 8 also fits the model, then go and check if n equal to 7 fits or not. You found out that n equal to 7 is not fits the model properly. Therefore, n equal to 8 is the correct answer. Not correct answer, is a good model though. How did we figure out n equal to 7 does not explain the model properly? We plot the residual plot, and we saw at when the degree was 7, the noise was high, but most of the points were away from 0. This is how we figured out n equal to 7 was not a good model. And then we actually settled with n equal to 8 would be a good model to share. Is this part okay?
Yes, sir.
Okay. So this is what residual plot is. Now, there is another way. So one way is to reduce the number of features. You manually select which feature to keep and or otherwise keep decreasing the degree of the polynomial. So manually you select what is the degree that you want to go, and then keep reducing, keep increasing the degree or decreasing the degree based on how your model fits the data set. The other one is regularization. What regularization does is that you want to regularize the parameters of the model. So we will see some regularization. Okay, first of all, if this is the point, so all red dots are the point, is green line, if can you tell me what is the residual plot for green line and blue line? How will the residual plot for green line and blue line will look like? Residual plot for the green line, green prediction, and the blue prediction. How will the residual plot will look like? People were able to follow, right? Is my question clear? How will the residual plot for the green prediction? So red points are the data points, and green is some, say, n degree polynomial, and the blue line is some m degree polynomial prediction. And I want to know the residual plot of the n degree polynomial model and m degree polynomial model. How will the residual plot for m degree polynomial or m degree polynomial will look like?
N degree looks like a 2-degree polynomial, sir.
Okay.
M degree polynomial, 4-degree polynomial.
Oh, no, no, no. The question is not what is the value of n or m. I'm asking about the residual plot. So residual plot is, this is 0. So residual plot is for each of the data point xi, you want to find out what is the predicted yi minus the true y. True yi. So this is what you have a plot. So for each x point, what is the error between the prediction and the true value? So this is the data point. So how will the green line, which is the nth degree polynomial prediction, and blue line is the mth degree polynomial. So what? How will the residual plot for both of these will look like?
I can say.
Or we can't. Can we say? Can we answer this question? The answer is, or we can't say just with this information. We need more information. Is this everyone thinks we need more information, or can we say we need more information? Okay, so we don't need more information. Both the residual plot for both the blue line and green line will look as y equal to 0 line. For every point, the error is 0. You see, the prediction, there's a green red point. The value of for value of x, this is the value of y, and both green line and blue line contains this point. So the error will be 0, right? For this point. Everyone can see? For both blue and red, both blue and green, the error for this point is equal to 0 because the prediction and the true value matches though, exactly match, right?
Yes, sir.
And similarly for this green data point too, both the blue and the green point matches. The y prediction matches exactly. And
Yes,
similarly
sir.
for all the data points, it exactly matches the prediction. So the error will be 0, right? Right?
Yes, sir.
Okay. So you can see that both green and blue line has residual plot equal to 0. Like literally everything is equal to 0. But if I ask you, which model will you choose? And choose is the nth degree model that you will choose or mth degree model you will choose? Which
N,
model?
sir.
N, right? Why? Because why did you choose N? Why did you choose N? But what are you actually doing for choosing N? Why not M? Both has a residual equal to 0. Because you chose N because it was more smooth and it has less sharp turns, right? You see these
Yes,
sharp turns in between. You suddenly see this really high value. Suddenly here it has a very low value. So at this point, as you suddenly see the very high value. So you choose this nth degree polynomial because it has more smoother curves and the value change was not very fast. Like nearby values don't change very fast. Correct? So the point here in blue curve has this high value, but in green curve it has very close value, very similar to what the previous value was. So the nearby points do not have very large change. That's why you chose green curve, right? Everyone is with me for this point? No, yes. Okay. So the reason that you see such thing, we call this is called a bias variance trade-off. So when you assume that it has low degree polynomial, you're assuming you are putting your own bias that you are assuming that, oh, it's a less degree polynomial. So this is has high bias compared to blue point, but it has low variance. You can see that this nearby points have very high value and low values already. So it's called variance though. And the higher degree polynomial has high variance. So the model complexity means, so x axis here is model complexity. Yeah, the degree of the polynomial. Okay, let's use something else. So say k degree. So k is the degree of the polynomial. So the higher direction you go, so the higher degree it becomes like 100, 200, 300, 400 is there, and this side is 0. So 0th degree to what is 0th degree? See, okay, what is 0 degree polynomial? Can someone tell me what is 0 degree polynomial? How does 0 degree x power 0? What does it mean? Y equal
1.
to theta naught into x power 0,
Yes, sir.
which is equal to theta naught.
Yes, sir.
So y equal to theta naught is a constant. This is how a 0 degree polynomial looks like. It's a simple constant line. For any value of x, you just predict the same constant, right? Yeah, is everyone with me? So for any value of x, since x to the power 0 is 1, so for any value of x, you are simply predicting the same constant theta naught,
Okay, sir.
right? So the model complexity here is the kth order polynomial, and 0 is here, and it has a higher value. You can go till whatever number you want to make. It's like infinity you can make. But what the point is that the more higher the polynomial degree you go, you see higher variance, which is like the nearby points will change very rapidly. So that you call it a high variance. If you have a lower degree polynomial, how if you want to fit a line here on these data points, this red dots. So if you have a 0 degree polynomial, it will fit this red line. Assume this is the red line is the line that it fits. You can see that this red line is not a good representation for this data point, right? Say this red line that you see is a 0 degree polynomial. Okay. This red line is a 0 degree polynomial, and you can see that there is the nearby points is not changing very fast. It's actually not changing at all. The nearby points is always the same. So you see the variance, the brown line is also close to 0. Assuming this is the 0 is here. So variance is very low, but the bias is very high. It means that you are not taking into account, you are putting your own bias, that you are assuming that the model is linear, but the underlying model is something else. So the higher the degree of model complexity, the lower the bias is, meaning the lower the training error would be, but the variance will suddenly shoot up. The close by points will become will change really fast. Okay. So when the degree is low, you have low bias. When the degree is high, you have a high bias. You have a high variance. When the degree is high, you have a high bias. So the best thing that you should be able to do is that there should be a point where you have low bias and also low variance. That is the point. That is the degree that you should be focusing on. That is the model complexity degree that you want. And in this case, the whichever degree it is, the green point is the degree that you want. It has bias is also very close to 0, and there is the nearby points are also not changing very fast. So it has also a low variance. So you want low variance and low bias, and that degree that that is the polynomial degree that you want. Everyone is with me for this point? Anything that you want me to explain again?
Yes, sir. Fine.
Okay. So let's move ahead then. So there are two types of regularization that we can do. So since there is like very high bias, so you can see that the bias will become low when you increase your model complexity. But if you keep increasing your model complexity, the variance is also increasing very high. Variance is also becoming very high. So what you can do, what people have figured out, that they can actually do a nice thing rather than trying to figure out the k directly. We will actually control the weights of the parameter. So here the weights of the weights of the model are this theta vector, right? There are, if it's a 4 degree polynomial, you will have four theta 4, theta 3, theta 2, theta 1, and theta naught. So all these different thetas are there, right? So you want to control the weights of these parameters. You want to control the weights, control the value or the size of the value of these parameters. We will see how it actually affects. So what you want to do is that you assume that it is a very high degree polynomial. You can assume, say, it's a 10-degree polynomial. And there are two types of weighing things. So the theta here is like W's though. Here we have, suddenly we have used W here. Okay, it should be theta. You can assume this is theta. You can assume W is equal to theta here. So for each point, so J, here I is the data. So say first data point, ith data point, and J is the order. So say you have x. Remember the x square is there, x1 is there, and x1 is there. So the first point is xi1. Sorry, 0. It starts from 0. So xi0. The second point is xi1, and the third point is xi3, xi2. So for 2-degree polynomial, there will be only 0, 1, 2. So m will be equal to 2. So m, you can assume it's a mth degree polynomial. Mth degree polynomial. Okay. So you fit yi minus summation over all xij's, which is x square, x1, x2. This is matrix multiplication. So it's simply a dot product between the two vectors. And theta, wij's are theta. It should be theta 4, theta 2, theta 1, and theta naught. So you multiply xi0 into theta, the 0th theta, probably the second theta, xi1 into theta j, and xi2 into theta naught. And that's what you are doing. It's simply a matrix multiplication, the least square, plus lambda times the weight square. You are adding this all the weights, so summation over all the theta i's whole square. Oh, sorry, j. So assume, because it's a m degree polynomial, so j equal to 0 to m. So what we did, so assume you have, so this is what we are doing, x into theta minus y bar norm square plus lambda times theta I whole square. I is equal to 0 to, since it's a mth degree polynomial, m. This is what I'm trying to write in Rich. You remember what our x is, the big matrix x, data matrix, into theta. If you do, it will become a vector. Then it will become the predicted value minus the true value whole square. You do. So how do you do it? It's a there are two vectors. You have subtracted and it's a whole square. So when I write this, it's a norm square though. A vector norm. Everyone knows what is vector norm? Do people know what is vector norm? They don't know.
No, sir.
Okay, so let me write. So at least this part, okay, I will explain what is vector norm. This part is okay, right? There is this vector and you are trying to do square of that vector. We will see what does it mean. But
Yes.
this is what I'm trying to write. So vector whole square, the error between the two vectors whole square plus lambda times summation over all the thetas I whole square. And you want to minimize this value. So initially we were just minimizing this, the circle term. We were minimizing the error between them. Now we want to also minimize this by adding this extra term. We call this extra term a regularizer term, and this is called a ridge regularizer because we are actually using theta i's whole square, the squared regularizer. So how do we estimate the norm of a vector? So if you have a vector, all these points, say the vector is z1, z2, z3, say there is only 3 dimension there, and you want to estimate the norm of this vector. How do you do? The value is z1 square plus z2 square plus z3 square. That's it. This is what it is. Norm square. So you are doing norm square. This is what it is. So if there is, the error is, so you actually find the error between the predicted and the true value, and you square each term and add them, and you want to minimize that. Plus, you also want to ensure that all the thetas should also be very small. It should not be very big, because the error should also be small, and all the thetas should also be small, because theta squares should also be small. Everyone is okay with this? How will it affect? I will come again, but I'm adding just this extra term there, regularizer term. Okay, let me rewrite it again. Let me rewrite. So the ridge loss looks like this. So norm of x theta minus y bar whole square plus lambda times, this theta is a vector, right? So norm square. This is what we are trying to minimize. So you want to minimize the error. This term is the error in the prediction and the true value, and this is the, you want to ensure all the theta should also be small. So you want to minimize the error, plus you also want to decrease the value of theta. So you are decreasing the value of theta. It will cause decrease the value of theta. So this is what you are doing. You want to minimize the error, plus also decrease the value of theta. This is one way. The other way is in the lasso form. Lasso is, you want to minimize, same, you want to minimize theta minus error, plus this time you want to minimize the sum of mod thetas. So this is like all the mod values should be minimum. So what does it mean? What does it mean is that you sum all the, say it's a degree 2 polynomial. So mod of theta 1 plus mod of theta mod of theta 2 plus mod of theta 1 plus mod of theta 0. So you want to minimize all the modular values of thetas to be small. Here all the squared theta should be small. Here all the modular theta should be small. So it's a different form of regularizing, but ridge does this, and lasso is mod ridge is square. That's it. So you continue to minimize the error, plus you also minimize the value of the theta. You can minimize the value of the theta by squaring each term of the thetas, or adding or modulo the theta value and minimizing it. We will see the effect. We will actually see a tutorial how is it actually having an effect, but we will try doing it now. But this is how we do. So regularizer term you can add with different values of lambda. So there is this lambda you have introduced another hyperparameter. You did not want to deal with the model complexity. What is the degree that you want to choose? Now you have to deal with another since you can choose any large degree now, but now you have to there is another hyperparameter called lambda, which we have to control. We will see the effect of lambda too. Here too, here we have another hyperparameter lambda, which you have to tune. Okay, so I think we can stop here and let's go into the tutorial part. I am sure that many people are confused that why did we add this? How did adding a regularizer term help reduce the model complexity? We will do this thing now. Okay. So we will first start with a linear regression. Is the size of the is the font size okay? Everyone can see the font size clearly.
Yes, sir.
Okay, so let's do this. So we are importing all the packages. So let's import all the package. And we will solve linear regression problem on this diabetes data set. So we have this diabetes X, diabetes, whether the person has, so X is the feature. So you have, let's run this. So here we have for person 1, we have the age in some number. Don't ask me how did this number come, but the age is represented in this form. Sex information is represented in this form. I don't know how sex became this number, but assuming that this is how it has been represented, the BMI, BP, S1, S2, all the other 6 different features, all are represented in some numerical form. So for person 0, we have this information about person 0 and its corresponding value of diabetes. So you can see that how what is the degree of diabetes it has. It has a diabetes or sugar level of 151. So person 0 has a sugar of 151. Similarly, person 2 has a sugar level of 75. And you can see that person 3 has slightly higher, with a higher sugar, it has sugar level of 200. So all this information is available. Now your goal is that given X information, given this information, can you predict if the person has diabetes or not? I mean, not diabetes. Whether the person, what is the sugar level of this person is. So everyone can see it's a regression problem because you have to predict a continuous value number now. Everyone is okay? This is a regression problem. You have to
Okay.
predict the level of sugar. Okay. So this is the level of sugar. Let's just consider that we can use all the features. Let's just consider we are only using the feature level 3, the third feature, S3 feature. We will only use S3 feature to predict the value or predict the sugar level. Okay. So we chose that X is equals to diabetes 3 and Y is the corresponding sugar level. So this is what we chose X and Y, and let's plot this. How does this plot look like? So we are plotting X. X is here. It's a BMI, and it's not disease progression. You can call it a sugar level. So you can see for each BMI point, we have the corresponding label of Y. So this is how the data points looks like. And we want to fit a line, we want to fit a model such that it best explains this data. Okay. Okay, so this is how the points look like. And okay, we will come to this matrix later. We will do this part. We will come this part again when we actually do. But something interesting is there. So you can see that our algorithm. So we learned linear regression as y is equal to some b naught plus theta naught plus theta 1 x. We learned this thing, right? So let's do the same thing. Okay. Let's do the same thing. I think let's write this equation in the same theta format, not in the beta format. I think beta format is confusing people. So theta naught in let's write theta 1. Let's use theta everywhere. So that okay. We have theta. And let's call this as theta. Okay. So now, so this is how the single for a single x equal to S3 and the corresponding diabetes value, this is how it looks like. Now let's use all the x's that we have. So we have the diabetes x. So this vector that we have, all features, 6 features plus there is this BAP, BMI, sex and age. We have all these information. We'll take all these x's values. So all 6 x values are there. We have corresponding thetas too. We are adding corresponding theta value too, right? So how will it look like? Let me write this equation. Let me write this equation here. Sorry. So we have how many values were there in x? So we have, say, call age is equals to x0, x1, x2, x3, x4, x5, x6, x7, x8, x9. So we write y prediction is equal to some theta naught plus x1 into theta 1 plus x2 into theta 2 plus x3 into theta 3, and since there are such 9 such values, so theta 9 into x3, oh sorry, x9. So you see for each person, so for each person P, the pth person will have 9 different values. So you have x9 for the pth person, we have x9, x8 for the pth person, and similarly you have x1 for the pth person and 1. So for pth person you have 10 different values, so 9 different values and 1 extra 1. Why? So you have, where did this 9 different values came from? So for the 0th person you have age, so first value, sex, BMI, BP, S1, S2, S3, S4, S5 and S6. So there are 9 different values, right? So all these 9 value for a single person is this, and we want to write so we want to y prediction is this transpose into theta. So all this big theta bar. So theta bar contains theta 9, theta 8 and similarly till theta 0. And you can see that the y prediction is equal to a linear equation. Everyone is okay with this part?
Okay, sir.
Okay. So all these things that you have seen is the higher degree polynomial, degree 2, degree 4. It's just that why are we not, what is the degree of this polynomial? It's still a 1 degree polynomial. It's just that it has multiple variables now. Okay, it has just simply multiple variable. It is still a 1 degree 1 polynomial because all the x's have degree 1. All the x's have degree 1.
Yes, sir.
It's a feature of this xp. For a single person, there are 9 different features. We are just taking each feature and scaling with this degree thing. If you want to make this scale each feature a degree 2 feature, so you have this 1 degree feature plus you have to add x1 square theta 10 plus x2 square theta 11, then it will become a degree 2 polynomial. And similarly theta what would be theta 18 x9 square plus there is something more theta 19 x1 x2. This is also degree 2, right? Degree 2 degree 1 1 2 degree. So this is how the 2 degree
Yes, sir.
polynomial will become. Like it will become a very big vector, very large number of features plus a very large number of theta. So currently all the examples that we did previously was there was only x has only one feature x. But what if x the person itself has multiple such features? Then if it has multiple such features, then the degree will become even more bigger. So currently we are just dealing with a degree 1 feature. Assume that we are dealing with only degree 1. So which has x1 theta plus x2 theta, x3 theta, x9 theta. And since it's a degree 1, we can write y hat prediction is equal to, no, not just degree 1. If we are writing for a degree 1 prediction as y hat is equals to all the features in the x person transpose times theta. Okay. Now, similarly, we can write for the entire data set x into theta is equal to y prediction, y bar. And what is this x? X will look like this. Say there are some 100 such features, 100 such data points. So for first data point, you will see, okay, let me see how we have written here. I just want to copy that part. Okay, one is at the end. Okay, so the feature will look like X. So there are 9 features, right? X9, X8, X7. For person 0, 0th person, X1 for 0th person and 1. Similarly, for first person, there will be the feature X1, X91, X81, 1th person, 7th feature. Similarly, it will go X 1th person, 1th feature, and 1. And similarly, for the last data, last person data, XN9, XN8, XN7, XN1, and 1. So all the data points. So we have this X matrix is a n cross 10 matrix, right? X is a n cross 10 matrix. There are 10 points, 1 to 9, 9 points, and plus 1, 10 points. And row vector, row is the number of data points. So X is a n cross 10 matrix. Everyone is with me?
Yes, sir.
And theta is just 10 different values though that you want to multiply. So x9 in this vector into theta will give you the sugar level of this person 0. X1, the person 1 data feature into theta will give you the person 1's sugar level. Similarly, the nth person feature into theta will give you the nth person's sugar level. Everyone is okay? And if this
Okay,
is
sir.
if this is the equation, the value of theta is x transpose x whole inverse
X transpose
y bar.
Y bar.
This is the answer, right? So let's see this. So
Yes, yes.
okay, so yeah, let's I think let me just rewrite. It should be theta. Let's write everything in theta because we have used theta everywhere. Okay. So you have this equation. So you have y equals to, okay, there should be one more. Okay, it's all okay. So I think it is. Let's just write it properly. It should be okay. Let's just write it this way. So you have the first term that you see here is 1. Okay, yeah. So you have theta naught into 1 plus theta 1 into x1. The first feature, which is age here, you can see the first feature is age. X2 into it was BMI, so X2 into BMI plus X3 into it was sex, so it was X3 into sex. Plus there are different such features until theta 9 into S6, right? This was the S6 feature. So there are so many of these features. You keep on multiplying theta for each of these features. And since y is equals to the this product of all the linear equation, so you can write this equal to y is equal to x into theta form. So the x is this big matrix that we created. Where is that big matrix? This is the big matrix that we created, right? And if that is the case, let me actually write it even better though. This is small x. Let's make it small x so that everyone can see. So you have for each xi's there are these values. So this is small y. It is the predicted y hat. So let's write hat y. So the predicted y is equals to theta naught into 1 for each of these values, and you have y equals to x into theta, and the value becomes x into x transpose. So the dash above is called transpose, though. You can write transpose too. You don't have to write. You can write it transpose. Write it transpose. So you have x transpose x inverse into x transpose y. So let's write this equation. So we know this value. So we have x. So diabetes of x into numpy. We created numpy. So if you want to see what is the value, you can see the shape is 422, 10. So diabetes x times numpy, if you do shape, the 442 is the number of data points and 10 is the 10 features that we have. Remember the matrix size is, so we have this 10 features. Okay. Oh, I see. So there are 10 features. So there is not a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, so there are actually 10 features though. My bad. So this is not x9, there is 10 features. X, the person 0 also has the 10th feature too. X0, 10. So the X matrix is of size n cross 11 though, not x n cross 10. So there is 10 features, 10 such features plus 1, it's 11. So so the X matrix is data size n cross 11 though. Okay, so you have this 10 features here. So you can see there are 10 features and 442 data points. But you need to add 1 at the end, right? So you so why is that sugar level? Diabetes to numpy. So you can see if you write y to numpy, you will see that if there are 442. So there are 442 such values. And in x, you have to concatenate the size, the x, the ones and x. So if you do this, it actually just simply creates one vector. So you can see it will create this one vector. It is just simply adding one everywhere. And if you see the shape of it, it is 442 cross 1. And x will look like this. Sorry, I think let's write x just single value. Oh, just a sec. Now you will see x is, there is 1 and all the 10 features that you see. It's just that in my case I added 1 at the end. You can always add 1 in the front. So 1 and all the different 10 features that are there. Similarly, for x equal to third person feature, you will see 1 and all the other values, all the other features that are there. Similarly, for say 100th person, you will see 1 and all the 10 values. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all the 10 features and additional 1 that we have to add. So x is now size 442 cross 11, right? Similarly, n is the number of data points, so it became 442 cross 11. And now your goal is to find this theta x into theta equal to y hat, and the answer you figured out that you need to do x transpose into x. So you did x transpose into x. So when you write at the rate in numpy, it means multiplication though. It's a this is how it is. You don't write multiplication. If you write x into x, x into x, it is not matrix multiplication. If you want to do matrix multiplication, you need to write x transpose the x at the rate into x, then it will do matrix multiplication. So x transpose matrix multiplication with x, and then you find the inverse of this. So inverse. Then you multiply with x transpose x. This inverse matrix needs to be multiplied with x transpose x, and then you need to remultiply with y vector, right? And then you will get your theta. Let's write this as theta. Let's just write it as theta. So you have your theta. Let's see theta. What does theta looks? How theta looks like? So this is what your theta looks like. Everyone is okay? So this is, you have estimated your theta. Now, okay, let's add predictions now. Let's just do prediction now. So prediction is very simple. So you have okay, I don't think we have. So you can see y predicted. What is OLS? Just for the time being, forget OLS. So y predicted is simply x times theta, right? X times theta. And if you do this, so you have this. So the progression measured the true value and the predicted value. So true value is 151, but you predicted 206. So error is 55 minus 55. Remember that you have only created 1 degree polynomial, and 1 degree polynomial may not be the correct thing to do. You may have to increase the polynomial degree, which we will see later. But if you just fit to degree 1 polynomial, you are able to predict, you are able to fit the true value is this, and this is your predicted value, and this is your error. This is what it is actually showing you. I will share this notebook with you where you can play with each of these terms. But what I wanted to show is that it's not just you are able to estimate theta. Even if you increase the degree of the polynomial, just by applying x transpose x inverse into x transpose y, you are able to estimate the value of the theta, and you can actually make predictions though. Similarly, if you okay, so if you plot the residual plot, so this is how the residual plot looks like. Why is it so? It looks like continuous, but it is not continuous. We can actually make it 0. You will see. This is how it looks like. Y equal to 0 line is here, and all the data points are like very high noise, right? You can see the residual plot is very noisy. They are not close to 0. Everyone can see that the residual plot is not close to 0. The values are very high. So degree 1 polynomial is not a good fit. You need to increase the degree of the polynomial to actually make it a good fit. I think, is this okay?
Yes, sir.
Okay, so now we can actually see that what we did is a linear regression. We can also use, this is like we actually solved that linear equation x transpose x inverse into x transpose y. Now we can actually use the scikit-learn package too, which is already available. So you first create your x dataset, y dataset, and you call linear regression model with intercept equal to 2 true, and then fit your model. And that's it, your linear regression model is ready. And if you run your model, here again you can see your okay, so let me just delete this. Your and your theta value. Compare this, your theta, your prediction and the model. Yeah, like directly using some package though. I'm directly using your package. So the intercept value, the theta naught value is 152. So you have exactly the same number, 152, 133, 48, 41, 60, matching till like multiple degrees though. Next value is minus 10, 0.0009. You have this number. It exactly matches, right? Everyone can see that all these numbers exactly match though. So you can use a linear regression package, some package that a scikit-learn package, or you can use the method that we learned, this method. Or you can directly call this method. X transpose X inverse X transpose Y. You get the same theta value. Correct? Everyone is with me?
Okay,
So you can call this, you can call the model, or you can use your X transpose thing that you have learned, the X transpose, X inverse, this value too. Both will give you the same answer. Okay, let me share this notebook first. Okay, I will share this notebook before. I want to just finish something more though. Okay, I want to complete ridge and lasso that we want to see how it is. For the time being, just assume that this is the data that we generate now. I will share both the notebooks. So say this is the data that you have generated, like some curve. You can see that it's a degree 5 polynomial, and I'm adding some noise in it. So it's a 2 plus 25 x to the power 5 plus some noise. This is some random noise. Okay, and you can see this is how the plot look like. This is degree 5 polynomial plot. Okay, so this is the data, and let's sample some data. So I am just sampling 25 such data points. Okay, so we have sampled 25 such data points. So what does this data points look like? So you have x dot shape. If you write, you see you have this 25 comma 1, and the corresponding y you also have. So you have the corresponding y. Y is also 25 cross 1. So for this, For this blue point, you have corresponding y. For this point, you have the corresponding y. For this point, you have the corresponding y. So for every x, you have the corresponding value of y. Now your goal is to find out the function that best explains this data. Remember that this is the data, this is the function that you have, but you don't know, you generally have, in general, you always have a data though. We don't know the true function. Your goal is to figure out the true function. So we have these data points. We want to figure out the function. So as usual, we first split your data into train and test. So you have 20% test data, so which has x test and y test, and you have x train and y train. And we see this both the data points. So your test data looks like this, and train data looks like this, the green points, and the test data is these 5 points. So you have these 5 points, and we want to find the curve that best explains the data point. Okay, so you can create, you don't have to create manually create x square x1. You can call this function called polynomial feature function. It will create a degree 1 polynomial, and you want to do linear regression. So you want to do linear regression with polynomial feature 1, and we did this linear regression here, right? We can directly call linear regression model and do our work, or you can do manually like x transpose x, which will give you the same answer. So I am now no longer doing x transpose x. I'm just directly calling the function package though. So from the package, I imported linear regression. I am creating degree 1 polynomial. I am finding the value, and I'm fitting the value and making prediction of this. And if you see, and then similarly, I also created degree 10 polynomial. A degree 10 higher, much higher degree 10 polynomial. And how will the prediction looks like? So you can see on training data, this is how the degree 1 polynomial predicts, and degree 10 polynomial looks like this complex figure. Everyone is with me? So you can see,
Yes,
at least
sir.
if you increase the degree, say let's make it like a degree 20 polynomial, or say let's make a degree not 20, let's make it like more higher, like degree 50 polynomial. So you see the degree 50 polynomial looks like even more complex, right?
Yes, sir.
So this is what happens though. If you increase the degree of the polynomial, it is only it has so many noise, it does not explain the data set properly. There is high variance in the data set. Okay, so let's look at the error that these models have. The simple model has an error of 33. Okay, there are so many points that are away, but the complex model has a very low error, 9. But even though it has a very low error, it does not explain your data set properly. And you can see this thing that if you actually do a test, if you do, how does it look like on the test data set? So you have this test data set, this 5 point that you had. The linear model shows that this value, but the complex model shows this complicated plot. It says, oh, this is how your plot will look like, 10-degree polynomial. And you can see the simple model on test data has low error, and the complex model has very high error on the test data. Why? Because all these points, it sees that okay, it is not predicting a continuous values. The nearby points can have very large difference, and that's why on the test data you see a very large difference here. I'm sorry, I'm going it slightly faster because I just want to finish this topic. If you have still some doubt, we can discuss again tomorrow. I will share both the notebooks though. So since this complex model, the nearby points will have very high variance. That's why when it is trying to predict, when I showed it some unknown data point, it's ended up actually predicting a very high difference. So as you see, the value should be close to 0, but it has predicted somewhere minus 300 or something. Right? For this point, it has predicted minus 300 or so. And that's why the error actually ended up blowing so high. So what you do to reduce, so let's do our plot again. So this is our 1-degree polynomial, and this is our 10-degree polynomial. And we want to decrease the complexity of the polynomial. So we will apply our ridge regression and lasso regression once again. So we have this. So we have this different polynomial degree. So we will start by adding degree 1 to degree 10. One thing we can do is that we will start fitting every degree that is there and see which polynomial best explains the data set. Okay. So you can see that on the test data. So when the bias is low, what is it? When you have less degree than 1th degree, both train and test have low value, but as you increase the degree, train and test value both decreases. They decrease. There initially the error was like close to 5 or 6, and then they decrease further. Initially it is the error is somewhere 9, and then it decreases close to 5. It decreases further, and then the test error starts increasing. Look, the train error keeps on decreasing, but the test error starts increasing very high. So the model has become very complex that for unknown data points, it is not able to predict at all. But for the unknown, for the trained data points, it's predicting very accurately, like close to zero error. And that's what we saw, right? When we increase the degree of this polynomial, where is this degree 10? So when we made it like a 50-degree polynomial, so you saw that all the training points, it is able to perfectly able to predict, right? So that's what I'm trying to
Yes,
say.
sir.
When the degree is low, there is some error, but as the polynomial degree becomes very high, the nearby points will end up actually not be able to predict, and you will see a very high error. So this is why the train error becomes very high, but on the test error becomes very high, and the train error is still very low, because on the train error it is able to predict accurately, but for unknown data point it just cannot predict. It is very high. So now we will apply lasso and ridge. So we'll first apply ridge though. So ridge is your this part, the square term, and with alpha equal to 0.1. So this here this lambda you see in the package, it is called alpha. You apply alpha equal to 0.1 on polynomial degree 10, and you see what is the on test data. The suddenly the okay, and the lasso, if you want to apply, you just call lasso package with alpha equal to 0.1, and you see the both. Now the test error, initially the test error on degree 10 was very high. Where did that test error go? Something around 11,000 was the test error. Now by adding this lasso and ridge value, the same degree 10 polynomial became a test error of 30 and the test error of 31. And if you see how the plot looks like, this is how the plot looks like. The complex model of degree 10 without ridge looks like this, and with ridge it looks like this plot. It looks very close to 10 to the power 5 degree polynomial, right?
Yes, sir.
So just by adding a ridge regression, you are able to ensure that the model is able to is able to reduce the complexity and is able to predict properly. Similarly, if you apply the same L2 regression on the test data, if you try predicting, now the model is able to predict properly. A 10-degree polynomial for 0, it predicted minus 300. Now it is predicting very close to somewhere 3 or so. And it is in the same shape where the data came from. So test is able to predict after adding regression, what is regularizer, it is able to predict your true function behavior. And that's, I think, okay. So what lasso does is that lasso will try to bring all the alphas close to 0. Whichever alpha is not required, whichever the thetas are not required, it will bring those theta values equal to 0. But in ridge, it will slowly bring all the theta values close to 0. It will never become close to 0. In ridge, it will always be close to 0, but will never become 0. Lasso will make everything, all the theta value equal to 0 as soon as it becomes very low. I think I will stop here. I just want to complete regularizer topic and want to introduce that adding ridge regression and lasso regression reduces the model complexity. That is the most important point that you should take away from it. and we also saw that through if you use linear regression package, the answer that you get by using linear regression package and by using the same method x transpose x inverse x transpose y, you get the same answer. And we did lasso regression, lasso and ridge, and we did uh, linear regression package and the true or by analytical calculation of linear regression gives the same answer. So yeah, this completes linear regression fully. Any doubt? I will share. Just wait, please wait for a while. I will share both all the tutorials on WhatsApp. Okay,
Okay, sir.
let me share. So any doubt if you have, please ask. I am here, so I can also answer if you have any questions there. Oh, lasso. Oh. Okay, can someone confirm if they can see both linear regression and lasso notebook?
Yes, sir.
Okay, I will also add today's polynomial regression that we covered. Just a sec, I will also share that PDF. 1 second.
Sir, I have a doubt.
Yes, please.
Sir, yesterday we saw polynomial regression.
Uh-huh.
On that, we say the n equal to 10 is overfitted.
Uh-huh.
But today, if we increasing the n value, it reduces the model complexity. How, sir?
Oh, okay, okay. I did not say that it reduces it. It actually keeps on increasing the model complexity. Okay. So you see, is my screen visible?
Yes, sir.
Okay. So you see, if you keep increasing your feature, so here it's a simple model, right? X equal to degree 1 polynomial.
Yes, sir.
And if you increase the degree of the polynomial, it has become a very complex model. So the complexity of the model has increased, right?
Okay, sir.
Now, even if you increased more, like let's add, make it 15-degree polynomial. Sorry, I think I ended up closing everything. I need to rerun. If you make it a 15-degree polynomial, I made a 15-degree polynomial, and you see the model complexity has increased further,
Yes, sir.
right? So what if you keep increasing the degree of the polynomial, the model will become very complex. It will become complex. But what I am trying to say, the one way to actually find out what is the good degree is to actually do manually assigning. Okay, degree 10 looks very high. Okay, let's start doing it. Let me show you how to do manually too. So you found that degree 10 is very complex, right? So let's decrease the degree. So let's go to, say, we will go to 8 degree. Let's see, 8 degree, how does, so do you think 8 degree explains the data set properly? Well, it looks okay, but still it is have very sharp turns. So let's decrease further.
Yes, sir.
So let's call it 6 degree. We will go to 6 degree polynomial. It looks better, right? It looks fair though. It looks better. Okay, some it is able to fit there and then go there and fit this. It looks better. Let's make it 5 degree. 6 looks better to me. 5 is even better, right?
Yes, sir.
Let's try fitting 4. 4 looks even. If which one will you choose? 4 or 5 or 6? Which one you will choose? I think I will choose 4 though. 4 looks much cleaner to me. It's more nice, smooth curves
Yes,
everywhere.
sir. 4 is better.
So what you are doing is that you are manually choosing the number though. So now I'm choosing degree 3, or degree 3 looks even much better. So what currently we are doing is choosing it manually by looking at the data and then manually tuning the parameter. We are tuning the degree of the polynomial, right? This is okay. This is
Yes.
all okay, good though. But if say this is, you can only do such thing when you have less number of features. Currently, we only had x equal one feature. If we had this diabetes like data set, multiple such features, we will not be able to train find these nice looking curve every time though. Or sometimes visualization is also not possible. In those cases, what we generally choose is that we make the model complex. So we have a complex model. Degree 10 is a sufficiently complex model, and then add a regularizer. So you have seen the degree 10 model, and we also saw that test error shoots up exponentially. If your model is complex, the test error went very high. So what we do is that we add a ridge with a small alpha. You keep the degree 10 polynomial, you have the degree 10 polynomial, and you add a ridge regression of alpha equal to 0.1. Or you do lasso regression with alpha equal to 0.1, same degree 10, you have less error. You have less error. Initially it was 11,000. Now it is close to 30. So which is less error. And if you plot your model, the complex model looks like so complex, but with polynomial 10 with ridge regularizer, you have become such a nice looking curve. You are able to decrease the complexity of the model by adding a regularizer. That is what I'm trying to say. That make your model complex, and even if the model is complex, if you add a regularizer, it will reduce the model complexity. The regularizer reduces the model complexity, and not other way around. Okay.
Okay, sir.
Okay. So any more doubt? Achha, even if there is, so we can take those doubts tomorrow. I think it's already 3 minutes ahead. Other people might want to go somewhere. So let's end today's class. And thank you, everyone. I
Okay,
have
sir.
shared all the notebook and the today's lecture slides in the WhatsApp group. I think, can someone confirm that they can see and they are able to download all these?
Yes, sir. It received.
Okay. Thank you again. So from tomorrow, I think there will be another person who will come to class and take the course. Yeah. If there is
Okay,
any
sir.
doubt, you can ask him. I will also inform him too. Thank you again. We can end the lecture then.
Thank you, sir.
Thank you.
Thank you, sir.
So we can end the lecture then.